G'day viewers. In this segment we'll talk about some of the fundamental limits for how quickly information can be sent over a physical channel or link. So when we build communication links, often we'll like them to have high performance to run as quickly as possible. So it's useful to know just how fast it's possible to build a link. In this segment I'm going to talk about two different results, the Nyquist limit and the Shannon capacity. As you can see, these are fairly early results. They've been known for a long time. They give us limits on what it's possible to achieve. So the real systems which are built are going to operate within these limits. These different results are expressed in terms of the key properties of channels which we might care about. The properties that are used are the bandwidth, B. That's important because the amount of bandwidth limits how quickly the signal can make transitions up and down and hence convey information. And the signal strength, S, and the noise strength, N. These are as measured at the receiver, how strong a signal they receive at the receiver. As you might imagine, the relative strength of the signal compared to the noise limits how many different signaling levels we can distinguish. More signaling levels will let us send more information. Let's see the results. So the first result I have for you is the Nyquist limit. This is for a noiseless case where we're just ignoring noise. The Nyquist limit tells us that the maximum symbol rate is 2B. A symbol is simply a waveform which is used to convey information. It might represent 1 bit, more than 1 bit if you have multiple signal levels, or even less than 1 bit in some cases. So a symbol is a waveform that stands for bits. Nyquist tells us that if we have a bandwidth of B, we can signal symbols at a rate of up to 2B. Here I've shown just a simple waveform, say that's the highest frequency we can send. That could encode 2 different bits per transition there, an up and a down, a 1 and a 0 I've shown here. Now if we also have different amplitude levels, if we have V different signal levels, that would be log to the base 2 of V different bits. For instance, if you have 4 signal levels, that will allow you to convey 2 bits with each level. 8 signal levels, 3 bits, and so on. Putting these two terms together, Nyquist tells us that the maximum rate we can send information across a noiseless channel is 2B multiplied by log to the base 2 of V bits per second, where V is the number of signal levels. Let's move on to the other result which we'll care about, really the end result here. This result is due to Claude Shannon. Shannon was a giant of early computing. In 1948, he put together a treatise called The Mathematical Theory of Communication. This was a landmark paper that put forth many of the key concepts and helped found a field called information theory. It told us really what information was, all sorts of things. Shannon, as well as making fundamental contributions to communications, also made contributions to digital computing and security. He was quite an amazing guy. He also had fairly wide-ranging interests. This picture shows an electromechanical mouse he built. The mouse, there are magnets underneath. The mouse runs on this maze. You can reconfigure the maze and the mouse will learn how to solve it. And this was a long time ago, so it was quite amazing. Shannon's capacity tells us the maximum information carrying rate of a channel, and it does that by considering the noise. Now, the number of different levels we can distinguish, signaling levels at the receiver, is going to depend on the relative strength of the signal that we receive. That signal is actually S plus N, the signal plus the noise at the receiver. The strength of that signal compared to the noise. If it's large, if that ratio is large, we'll be able to distinguish many different levels. In the picture here, you can distinguish maybe 4 different levels. So if I receive something here, maybe I can know that it's most likely that a 1 was sent. Because if I sent a 1, the noise would only have moved it up and down by a bit, and so 1 is probably what was sent. On the other hand, if I receive something here, it's probably the case that I sent a 0. Keep in mind that this noise is a random process. The arrow here is only a depiction of how big it is on average. So at any given time the noise could be larger, and we may have some errors that are caused when our assumption is wrong. We'll have to deal with them later. The signal to noise ratio, or S divided by N, is typically expressed on a log scale because it can take on a wide range of values. So if, for instance, we have a signal-to-noise ratio of 1,000, that's often written using our little formula here. We express it on a log scale by taking log to the base 10 of the ratio and multiplying by 10. That's often written as 30 dB. Log of 1,000 is 3, multiplied by 10 you get 30. There are many other common SNR values in decibels that you might come across. So as you might imagine, 100 goes to 20 dB, 10 goes to 10 dB, 2 is a common value and that goes to 3 dB, and so forth. Okay, armed with this understanding of the signal-to-noise ratio, we can talk about the Shannon capacity. This is a limit for the information carrying capacity of a channel. The limit, the capacity, is given by the bandwidth, our factor from before, multiplied by log to the base 2 of 1 plus S on n, where S on n is the signal-to-noise ratio. This bit in parentheses, you might recognize this as what we receive, S plus n divided by n. That's really S on n plus 1. This bit, log to the base 2, is converting to bits. And then we'll multiply them by the bandwidth. The Shannon capacity is really quite fundamental for a channel. Shannon showed that it is possible to transfer information reliably over a channel up to that rate, but no higher. This was quite revolutionary at the time, when there always seemed to be errors on channels, and the only way you could get rid of them was by sending a stronger signal. Shannon really told us that in theory there exist codes so that you will be able to send information reliably across channels up to a certain rate, even for whatever signal-to-noise ratio you're sending in. So just to sort of wrap up on this segment, I'm going to give you a little perspective on wired versus wireless links. We've now seen pretty much everything we need for the physical layer. Error coding is a big subject that I'll get onto next, but we've seen how to modulate signals and send information across links. Yay, we're well on our way. There is a big difference, however, between wires and fiber and wireless. I would characterize it this way. With wires and fiber, you can often engineer the parameters. You can fix the bandwidth you're using by the quality of the wire and the signal-to-noise ratio. You might send a certain value in and say the cable can be no longer than 100 feet. This means that you can fix the data rate. On the other hand, wireless is quite different. You might be able to fix the bandwidth you're using as part of the design of the system, but the signal-to-noise ratio will vary greatly. It says here up to a factor of 60 dB. If you do the math, that is 1,000,000. That's a lot. That might be the difference between signal strength in being close to an access point, an 802.11 access point, and receiving information quickly, and being far away on the very edge of reception, but still being able to use it. Given this wide variation, the signal-to-noise ratio is going to vary a lot. We can't design the system for the worst case, or it will always run at a rather slow rate. Instead, the name of the game in wireless is adapting the data rate to the conditions you find. So just recapping, for wires and fiber, we engineer the system to give us a certain data rate that we expect and spec. For wireless, we need to adapt to the SNR. And finally, just to put some of these things together, I can now give you an example. Let's talk about a link that many of you know about, maybe you're using right now, DSL or digital subscriber line. This is a widely used technology for providing broadband internet to homes. There are many different variants of it, and they run at tens of megabits per second. DSL reuses the twisted pair telephone line that goes to the home. So here's the local telephone exchange, and there might be two different lines that go to the home. Now, it turns out that the telephone is only using the bottom 4 kilohertz of this wire, but the wire has a bandwidth of up to 2 megahertz. We can reuse the higher portion of that bandwidth, which is currently unused, to carry data. That's exactly what DSL does. Because it's been refitted to the existing telephone wire rather than designed from scratch, it has some of the characteristics of wireless too. As you might imagine, this close house, if I'm close to the exchange, I might get a high SNR, compared to if I'm a long way away, the signal might be weaker and I might get a low SNR. because the signal's attenuated by the time it's got there. When I've got a low SNR, I might get a rather small data rate compared to the other house, which could get a fast data rate over DSL. This is why when you want to buy DSL, sometimes your provider will tell you that you're a long way away from the exchange and they can only sell you a plan that goes this fast. Or that you're lucky, you're close to the exchange and they can sell you a plan which runs at the maximum rate. Here are a few more details for DSL. DSL, because it is sending at frequencies above the voice band, uses a form of passband modulation. I'm not going to go into all of the details, that's sort of a whole course. It does use a technique called OFDM, which turns up many times in communication systems. You can read a bit about this in your text if you're interested, just for fun. DSL divides the frequency band to provide separate bands for upstream and downstream communication. You can see here that it uses 4 kilohertz for voice, that's not much, and then it divides it into different portions for the upstream and downstream. DSL, or actually the picture here shows the frequency plan for ADSL2, which is a fairly garden variety version of DSL. It allocates more bandwidth to the downstream version than the upstream version. That more bandwidth is going to translate into a higher number of bits per second. The A in ADSL stands for asymmetric. This asymmetry is deliberate to allow you to download information from the internet faster than you can send it. The modulation that's used inside these bands varies both the amplitude and phase of the different carrier signals. It's called QAM. You don't need to remember that though. If you're now all of the different signals in here, they can send information at different rates. If you have a good portion of this band and you're fairly close to the exchange, you've got a good quality signal, you might get a high SNR and you might be able to send it up to 15 bits per second. Sorry, up to 15 bits per symbol. So that's a lot of different amplitude and phase levels, 2 to the 15 at least, to convey that number of bits. On the other hand, you might have a different band, part of the frequency, which might be bad, not working very well. This one's nice and solid, let's say, and the other one's not working very well. This particular part of the band might give you a low SNR, in which case you'll only use it to send 1 bit per symbol. So this is how you can get different rates over DSL. Okay, well, we've now seen a lot about the physical layer, and shortly we'll move on to the next topic of error coding.